polarity, that is a singularity. Black hole is a singularity. Because now, when Earth becomes a black hole, you throw even a photon from its surface, it will fall back. Okay? It will not escape. Because escape velocity has now become equal to the velocity of light. So it would never escape. It would just fall down. And the limiting case of escape velocity equal to the velocity of light. Right? So that is what we understand about a black hole. Now, if you make a plot, my talk is always based on first year physics. So you make a plot of the gravitational energy. This gravitational potential energy phi is minus dm by divided by modulus of x. So m is sitting at the origin and you measure the potential energy at x. And you make a plot. So it's mod x, so it would be a symmetrical curve on both sides. Okay. Now if you increase m, the potential energy band would be deeper. You increase m further, it would be deeper and deeper. So as you increase m, your potential energy band goes down and down and deeper and deeper and deeper. Right? In fact, if you do it, once I did this exercise sitting in the train somewhere, traveling near Agra, and I plotted, then my paper was always short of what I wanted to plot. You could not plot even a few points as you increase m. And I would recommend that you should do such exercises for brain jogging. Then, so what happens? Now think of the mass of the Earth or the Sun or a massive black hole or a supermassive black hole. Now that singularity would be so deep. Once here, if you are inside the black hole, I mean, so the singularities exist even inside the black holes. The time, the length scale now becomes of the order of 10 to the power minus 33 centimeters. If I talk in terms of a supermassive black hole and potential energy band of that, so it would be like that. So singularities, so this question of singularity is very important. That makes me think about some further generalizations of gravity. And now, one of the remedies that immediately comes to my mind, that in nature I have heard very beautiful symmetry called as supersymmetry. Supersymmetry is a symmetry that rotates bosons into fermions and fermions into bosons. Very simple. So far you have not experimentally verified it, but it's the most beautiful theory. And maybe, I'm sure it would be experimentally verified. But even for the hadron physics people, I can tell you the references from Stan Brodsky and company name I might recollect. Stan visiting Yale University during our conference. So he has some very fundamental papers on supersymmetry in hadronic physics that people might like to look at. So it's possible to identify, he gives possibilities how to identify supersymmetry in hadronic physics, strong interaction physics. Okay. So there is a good possibility of, I mean, this is the simplest example that I have given. You don't have to wait for everything to be detected by Large Hadron Collider at CERN, because it takes billions and trillions of energies to center of mass energy to reach those scales. And you need the similar amount of, proportionate amount of money for constructing everything, and you have physical limitations then. So one should then think of, I have a friend, Anupam Majumdar. He is a professor at Groningen University, very next to the place where we used to visit in Oldenburg, northern Germany. It's 2 hours drive from there. And he visited us a couple of times at Oldenburg, and I heard many times his talks. And now he's doing a tabletop experiment. His team, he is a theorist, but he collaborates with experimentalists also, to look for the experimental detection of graviton. So just like you have photon for electromagnetism, the force carrier of electromagnetic field, electromagnetic forces, electromagnetic interaction. For gravity, it's called as the graviton. I just come to it in more details a little bit later. It's a spin 2 tensor particle. So, if one can look for experimental discovery of a graviton, recently one of the common friends, You might recollect Rahul Basu, you recollect? So Rahul Basu, if you look through his Facebook, one of my friends there, Professor Purushottam Chakravarti, might recollect. So he has recently written, maybe in the last few days only, something on the possibility of experimental detection of in the two tabletop experiments for the graviton. So I would encourage people to look at these things. If you, I mean, there could be a very close mind approach that I keep dreaming about what CERN will do for me, what Large Hadron Collider will do. It has many limitations. Your mind cannot stop thinking because you don't have possibility. Okay, if you cannot have bread, you would like to think of rice. If not rice, something else. Okay, so this is one thing. So if you, why did I talk about supersymmetry? If I introduce supersymmetry in the standard model, I can construct the whole supersymmetric standard model. What happens? Now my particle content would be doubled. I would have a super partner for each and every particle. Okay, let me not go into much detail. The particle content would be simply doubled to that of the standard model. Okay, standard model, each and everything stands experimentally verified. Very up to several digits. So, but then why do you worry about that? You just write the self-energy diagram for a Higgs particle, one of the media, and popularly it came to be known as a God particle. You need Higgs. So standard model has only one Higgs. I will tell you just now the possibility where you will have 70 Higgses in your theory. We wait for a few minutes, and therefore I was not able to make commitment on time. So I try to be honest with the original time that was given to me. So if you now write down the self-energy diagram for a Higgs, in a standard model, it's quadratically divergent. In a supersymmetric standard model, you have two such diagrams, and both of them are quadratically divergent, but in the opposite direction, so they cancel each other. So that means now this would be a divergent process. You see, for in field theory, you need to work on renormalization theory. If you like, I can give a series of lectures on that sometimes, if and when possible. I used to teach in quantum field theory at the university. So my friend Samantha is sitting here. He has been through my lecture courses, and so very interesting, very important calculations. And so if you increase symmetry in your theory, divergence is reduced. That is the conclusion. Okay, so the same happens with supersymmetric standard model. But now, if you go into the theory of supersymmetry, what you find that each and every supersymmetric field theory, no exceptions, they are invariant under rigid supersymmetry transformation. So here, the transformation parameter is a constant. Of course, it's a constant spinner. So this epsilon or epsilon bar, it's constant. It's not a function of x nu, so it's not a field. I would just now come to its generalization. So when the spinner is constant, it's a constant spinner, every supersymmetric field theory would be invariant under only and only rigid supersymmetry transformations where the transformation parameter would be constant spinner. That is the conclusion. So this means my supersymmetric standard model, which is also a supersymmetric field theory, would not have a gauge symmetry, the local gauge symmetry, the true gauge symmetry which leads to the conservation of charge. We know that if you measure the charge of an electron here in this auditorium or in Manipur or in Delhi or in New York, it would be the same. That is what we mean by its conservation. It would be same today, it would be same 100 years later. That is the meaning of conservation. So it is the consequence of the so-called gauge symmetry of the theory. If your corresponding field theory is invariant under local gauge transformations, local supersymmetry, it would lead to a conserved charge. And that conserved charge, for example, in the QED theory, would be the electronic charge that you measure everywhere. Milken White drop experiment to do the masters of physics also. Okay. So physics is all related. It's all from beginning up to first year up to all the final years, PhD and beyond. There is no classification for me. The fundamentals remain the same. Okay. So this is the importance of the gauge symmetry and its consequence, the conjunct chart. Now, in a supersymmetric standard model, I said yes, it has several advantages, but then it does not have gauge symmetry. It does not have local symmetry. Gauge symmetry has to be a local symmetry, which means the transformation parameter would be a function of x mu, so that this would be a field by itself. Okay. Now, very good. So we would try to look for also the standard model as well as supersymmetric standard model. It does not include gravity by any chance. You describe it in terms of flat space-time manifold in terms of Minkowski space, 3 space 1 time in the 4 dimensions. So this is flat space, so it means no gravity. All right, fixed metric times and no gravity presence, no presence of waves. So there is no question of thinking about graviton and gravitino and other things within supersymmetric field theory, supersymmetric standard model. So what I would do, I have at my hands one fundamental theorem from PANE24. She was a woman physicist, by the way. If you look at her name and her work, I mean, your entire physics would collapse without her. Okay. So what you use in classical mechanics, all these symmetries, it's being given by PANE24, a German woman physicist.